See, we have intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Archana Soam with us today. Hey, Archana.
Hi, Frank.
How are you today?
I'm good. How are you?
I'm doing well on this spring day, spring 2021 day. And I'm in Phoenix. And where are you at?
Okay, so I am a postdoctoral fellow at Sophia Science Center in NASA Ames in California.
Okay.
But I'm working from Boulder for some time because my husband works in Boulder.
Oh, okay.
So yeah, I'm a postdoctoral fellow at Sophia Science Center and mainly working on NSF grant with Dr. P.G. Anderson.
Very cool. Very cool. Very cool. So is that an office you're at? Looks with the bricks or institutional.
This is my office created in my home, in my bedroom.
That is awesome. You even have a plant.
Yeah, I have plants. Yes.
Very good. Very good. Cool. Awesome. So do you anticipate going back to Ames, or are they still in a sort of a lockdown state, or what's the
Yeah, they're still like a mandatory telework stage. Okay. But if somebody has like something very important, they have to apply for going there, like for permission and all. I mean, I did not have to go to office for something, or so I have everything with me and I'm just working from here. But my plan is I'll go back once I'm vaccinated, and I hope in April everybody will start get vaccinated. Yes, because I don't want to fly without that.
I can understand that.
Especially to Santa Clara County. The situation in Santa Clara County was not good.
Okay. I am vaccinated, so I got my second shot about 2 weeks ago now.
Nice.
So I should be good.
I heard a lot of scary things about second shot, but looking forward.
I had more issues with the first one, and it was just like somebody took their knuckle and just banged me right in the arm, and so my arm was like, but the second one was I had almost no reaction at all to the second one. Nice. I did the Moderna.
Nice.
So it was all good. So I'll keep my fingers crossed, and hopefully you'll get yours soon.
Yeah.
I hear they're dropping the age dates down to 16 now, and
yes.
So it's really just a matter of getting the supplies out and getting people lined up. So that's good. That's good. Awesome. Archana, what do you like to do for research?
Okay, so I started my PhD with optical polarization in star-forming regions, mostly galactic astronomy.
Okay.
So I started working on polarization of starlight and understanding and using that to understand the roles of magnetic field in the formation of stars. So that was the main thesis idea in my PhD. Cool. So I did my PhD from India. So there we had one optical polarimeter, and I was just constrained to use optical polarization observations only. So in one wavelength, you're not going to get much information of magnetic fields. So when I did my first postdoc in South Korea, in Korea Astronomy and Space Science Institute, there I started doing sub-millimeter polarimetry using JCMT, ALPA, and also near infrared using SERPO. So like 3-4 wavelengths I started working on, and I also became a active member of BISTRO survey. It's mapping B field in star-forming regions, all gold belt star-forming regions. Right. It's led by Professor Derek Ward Thompson. So there I learned a lot about more about multi-wavelength magnetic fields in these star-forming regions. So my research area is to understand roles of magnetic fields in star-forming regions, why and how magnetic fields are important to study, and how they're either enhancing or either supporting or regulating the star formation rate of our galaxy. So right. It's mainly magnetic fields and star formation in one sentence.
Cool.
This is my research area. But in my second postdoc, I joined my second postdoc in Sophia Science Center in mid of 2018. There I started working with VG, who mainly does grain alignment, how we get polarization of starlight, that is due to grain alignment in interstellar medium. So now I'm mostly working on grain alignment, characteristics of those grains, and how we can use the polarization measurements to understand more about interstellar grain properties actually. So
Awesome.
all about polarization and magnetic fields.
Cool. And that is going to bring us to this very lovely APJ article, February 2021, on the collisional disalignment of dust grains in illuminated and shaded regions of IC63. And Archana, take us away.
Thanks, Frank. So as I said, that until 2018, I was just using polarization measurements for mapping magnetic fields in the interstellar medium, the star forming regions and low and high density regions and all, and understanding their morphologies and strength in the interstellar medium and their role when we compare the magnetic energies to other energies like gravitational energy and kinetic energy. For the first time in this paper, we thought that can we use polarization data and the gas measurements we have? Can we use these two measurements to understand what is happening to the grain alignment? So this paper is all about understanding how collisions of gas and dust are creating some kind of disalignment of the interstellar dust grains. In PDR, photo dissociation region IC63, which is a very nearby PDR in H2 region, sharp plus 185. I had already published densely sampled magnetic field morphologies on this region in 2017.
Okay.
And so we thought, okay, let's use that data, combine polarization data with gas measurements, and see what we can do to understand grain alignment. So the idea behind this paper is that wherever there is warm and cold dust, and wherever there are grains, we always have gas and grain collisions. So this is the first observational attempt or evidence to see when gas and dust grains collide, they can disalign. I'm not using word misalign because I don't know. People like using this word disalign in this polarimetry. How they can disalign the aligned grains. So before diving into details, let me just give like a flavor of how dust grains get aligned in interstellar medium and how we get starlit polarization.
That's another good idea.
So dust grain alignment theory was like it's a very old and very interesting problem, but recently established theory of grain alignment is that radiation, interstellar radiation field, applies torques. So this radiation driven torques in interstellar medium helps in spinning the asymmetric paramagnetic dust grains. So these two are important conditions: asymmetric paramagnetic dust grains. So they give this the rotational torque to these grains and they start spinning. Then these spinning dust grains have their angular momentum, and because they are paramagnetic in nature, they have some kind of paramagnetic movement, magnetic movement in them. So that angular momentum gets aligned with the interstellar magnetic fields. We have interstellar magnetic fields everywhere. So the magnetic fields there plays a role of like external force, which helps these spinning dust grains to get aligned in such a way that grains angular momentum gets aligned or parallel to the magnetic fields, because that is the minimum energy state of the grain. So grains start spinning by interstellar radiation fields because of the torque from the interstellar radiation field, and those spinning dust grains get aligned with the magnetic fields in such a way that their minor axis, because that's why I said asymmetric, elongated. So their minor axis gets aligned with the magnetic fields. So now the picture is we have elongated paramagnetic dust grains aligned with magnetic fields, and their minor axis is parallel to the magnetic field. So we have a system like this. We have a polarizer now sitting in the interstellar medium. Now let's suppose in our line of sight, let's suppose we have this array of aligned dust grains. Suppose the grains are get illuminated by the background starlight.
Okay.
And that starlight gets partially polarized because the light, which is facing the longer axis of the grain, gets dichroically absorbed. And we have some light, the light which is parallel to the minor axis or smaller axis of the grain comes out. So we have kind of partially linearly polarized light coming out of these aligned dust grains.
Nice.
Okay, so now this component of light, if we can map this component of light or this component of electromagnetic radiation, because we know that component is parallel to magnetic fields. So if we are able to map that component, we are able to map the magnetic fields. So this is whole grain alignment and polarization of starlight.
Right.
So now in this paper, we have polarization measurements from optical, V and R band, and we have molecular hydrogen measurements, molecular hydrogen fluorescent measurements in this particular region. And we also have HCO plus measurements. So before going to observations, in this equation one, so the broad idea is that, okay, if there are grains, if there is gas, can this gas grain collision disturb my alignment pattern? And
Right.
if it disturbs my alignment pattern, certainly my polarization will go down, right?
Mm-hmm.
So this is what we want to test with the observations. So in this first equation, we are saying that not we are saying, actually it is already said in theoretical papers by Alex Lazarian and Thiem Huang in 2015, that this change in the angular momentum depends, or change in this alignment pattern in a broad sense depends on the either on the far infrared emission damping or the collision of gas and dust. So far infrared emission damping is very minor. So we should mainly worry about gas and dust collisions, which can affect our grain alignment pattern and affect our polarization. So equation 2 and equation 3, equation 2 shows that grain alignment mainly depends on RAT, which is radiative torque alignment.
Mm-hmm.
And equation 3 also shows that grain alignment also depends on the formation of molecular hydrogen. So this is very interesting pattern here. So before RAT came into picture, because before RAT was established, Edwin Purcell in 1979 proposed that, as we know, that molecular hydrogen forms on the surface of the dust grains. So when this molecular hydrogen leaves these dust grains, they give a kind of back thrust or torque, or and which is known as rocket effect, phenomena like rocket effect. So when they leave the surface of the dust grain, they give a back thrust, and it helps the grains in spinning. So if we have radiation torques and if we have molecular hydrogen formation on the dust grains, these two phenomena can help our grains to start spinning. And spinning is important for grains to get aligned with the magnetic field. So at the very first, we should need something which can which can help our grain to start spinning. So molecular hydrogen formation can help in starting spinning of the dust grains.
Cool.
Because in this work we have polarization observations, we have molecular hydrogen observations, so and we have gas measurements from HCO plus. So we want to see that. So we want to uh, prove or kind of try to put evidence for two phenomena. One, if there is molecular hydrogen, then is it the formation of molecular hydrogen, is it affecting my polarization amount? So the place where I have maximum amount of molecular hydrogen, do I have maximum amount of polarization? Because more is the molecular hydrogen, more will be the chances to get grains spinning, and more will be the chances to get it aligned, and more will be the polarization. So we want to check a kind of correlation between molecular hydrogen formation on dust grains and alignment of those dust grains to give us polarization.
Right.
So that's the first problem we are addressing here. Other is that because we have HCO plus gas measurements, so we want to see, as my HCO plus gas intensity increases, is it increasing the collisions? Because gas intensity increases means there is more gas means more chances of collision. And if there are more collisions, is it affecting my polarization? So these are two problems we are addressing here.
Yep.
So in observation section, we used most of the data which we published already in 2013 and 17 paper, the polarization data in optical V and R band.
Yep.
This is from some data which was published by VJ in 2013 was from Nordic Optical Telescope in La Palma. And the instrument's name was Turpol. I used most of the data from my PhD work, which I published in 2017. That data was in R band using an instrument called AIM-POL, Aries Imaging Polarimeter, on 1 meter glass telescope. So that was the optical imaging polarization data. In section 2.2, we have described that we have used some optical spectropolarimetry data also, which was already published in 2013 work of BG. So this was already published data. So we are just doing different application, using this data for different application.
Good.
In section 2.3, this data was not already published. This is the data observed by Karma in rotational transitions 1 to 0 in HCO plus,
Right.
and in the same region, in same nebula IC63, and at the same locations where we have polarization measurements. So this was a coincidence. I had lots of data, and BG said, my current boss, he said, oh, I have lots of gas data at this location. Let's see what we can do. And so these observations were done by our collaborators, I think in 2014, much before I joined here, and that data was just sitting with us. If you go to section 2.4,
2.4.
oh no, we don't have 2.4. Sorry.
Don't have 2.4.
So I think I did not talk about H2 data because that is very well described in the observation section of 2013 paper or 2013 paper. So H2 fluorescent images were obtained from CFHT telescope. So it is hard, it is very hard to detect molecular hydrogen in interstellar medium because of its polarity. So PDRs are the regions where we can get pure rotational or raw vibrational transitions of molecular hydrogen, because there we have lots of radiation dissociating molecular hydrogen and then forming them again. So we have, so that's why and just before section 2.2, I have this one paragraph on H2 observations from CFHT, Canada, France, Hawaii telescope, just before 2.2. Yeah.
Okay.
So we have three data set: optical polarization, H2, and HCO plus. Now we can move to results or figure one if you want.
Let's do figure one. We've got two figures. We'll go to the first figure first.
Yeah. So this is molecular hydrogen raw vibrational. So vibration V120 and S1, which is 3 to 1. J is equal to 3 to 1 line.
Okay.
So this emission line was observed from CFHT, and you can see the structure of the cloud. It is like coming diffused in northeast and getting brighter and brighter in the southwest. And there is a white arrow there towards the nebula, towards the nose of the nebula, I should say. That is the direction of the radiation coming from gamma gas. Actually, this nebula is situated in a expanding H2 region. Its name is Sharpless 2185. And the source responsible for that H2 region is gamma gas, which is a B-type star. So that this white arrow shows the direction of the UV radiation hitting this nebula from gamma gas. So it is illuminating this nose part of the nebula, and that part is known as PDR, photon dominated or photon dissociation region.
Okay.
So this is H2 emission continuum image, and if you go down to the bottom panel, this is the location of the HCO plus emission in this nebula. Again, the direction of the arrow shows the direction of the radiation coming from gamma gas, and you see this very nice nose-like structure, or this kind of stream coming out of the PDR. It is very well seen in H2 and HCO plus. So we have very good emission of both the lines H2 and HCO plus at the similar locations in this nebula.
Right. Okay.
So
good.
Up to now, if you have any question or anything, just let me know. I'm sorry if I'm running too fast.
I'm with you.
Okay.
I'm good.
Okay. So these are the gas emissions. I'm not showing the polarization patterns in this nebula because that has already been published in 2017 in detail. I'm just using that catalog of mine. So if you go down, before going to my results, let's check this figure 2. So I'm going to talk a little bit about the history of this figure 2. Figure 2 is a rotation diagram made for this cloud IC63.
Okay.
from the pure rotational H2 molecular hydrogen observations taken with ISO SWS spectrometer from by Thi et al. In 2009. So he observed S0 through S5 lines, all pure rotation using ISO in this cloud. And then he constructed a rotation diagram based on his fluxes he observed. And that because we know that rotation diagrams, and if we have the Einstein coefficient and other information, we can always get idea of temperatures, gas temperature in that region. So this figure we took from there. Actually, Thi in 2009 gave a very exciting hypothesis about this cloud. He said that this cloud, the PDR region of this cloud, where he did these observations, has two components of gas. One is warmer and one is hotter. So 106 Kelvin, the T excitation 106.5 Kelvin, he's saying is a warmer component of the PDR, and 685 Kelvin, he's saying that it is a hotter component of the PDR. So we thought that we are going to do some test on molecular hydrogen formation, like alignment of grains by molecular hydrogen and disalignment by HCO plus gas. Can we also see that what is the rate of that alignment, or what is the rate of disalignment in different temperature regions?
Right.
Okay. Or can our results also support his hypothesis of two temperature components in PDR? So I'm introducing this figure here to tell the readers that, okay, there is already one hypothesis on this PDR that there are two temperature components. With our observational data, which is not H2, with our polarization and other measurements, which is not pure rotational lines, can we do something to support this hypothesis, or can we just reject this hypothesis? So this is one hypothesis we are addressing here. So now let's go to next section or next figure.
Next figure.
Yeah, let's go. So let's go to. Sorry, Frank. Let's go to section 4. Yeah, just on previous page. On previous page.
Previous page.
Go to previous page. A page before this one. Yeah, above. Yeah, 4.1. 4.1.
Okay.
So in this section, section 4.1, I am talking in detail about the grain alignment by Purcell effects. So this is what I introduced in the introduction, that Edwin Purcell emphasized on the fact that formation of H2 give a rocket effect to grains, and that rocket effect helps in spinning of the grains and then alignment of the grains, and then that's how we get polarization. So I'm talking in detail about what is that Purcell effect and how it affects the grain alignment of interstellar medium. So now we can go to next figure.
Okay, there's your rocket effect right there. Okay.
Please feel free to interrupt me if you have any question in the middle.
Oh, you're rolling great. It's good. I'm with you. I'm following. Go ahead.
Okay. So figure 3 is a deliberate stretched image of HCO plus emission. In this figure, you can see these clumpy structures of HCO plus, like this reddish and greenish and yellowish clumpy structures. So the reddish part shows the higher density of that clump, and the density goes down towards the greenish color and the yellowish color. So this stretching of HCO plus image was done deliberately to see the clumpiness in the PDR. So now on this image, we have also showed these white and blue and red dots with numbers.
Okay, yes.
So these are the stars where we have polarization measurements exactly at these locations.
Okay.
So the blue stars are the stars which are categorized. Oh, okay. I should not call them stars. Okay. Imagine there is a layer of PDR, because everything we are looking in the plane of the sky. Imagine there's a layer of the PDR and there are stars shining behind that PDR, right? So that light, so when the light is coming from behind, okay, not behind in the line of sight, behind in the plane of the sky.
Yes.
So if you remember that I showed the direction of the UV radiation from south to west.
Yes.
So the side of the clump, these white arrows. So if you go back to that figure 3 again.
We got a little bandwidth lag. That's okay.
So the direction of the radiation is this white arrow. So now whenever I say behind and in front, I will talk about in context of this direction of FUV radiation. In that figure, the stretched figure, I'm showing those clumps. So the part of the clump which is facing this direction of FUV radiation, I'm calling that front direction. And the part of the clump which is not directly facing this radiation, I'm calling that behind the clump. So if you go back to figure 3 again.
Okay.
So these red, blue, and white dots are the lines of sights where we are getting polarization.
Got it.
Okay. And these dots are, so blue dots are the locations which are not directly facing the FUV radiation direction. It is behind the clump.
Okay.
But the red dots are the locations which are directly facing the FUV radiation.
Okay.
This side, yeah. Like if you see number 46 and number E.
Right.
So number 46 is directly facing FUV radiation and number E is behind the clump. So that's why I'm calling behind. It's not in the 3D behind, it's 2D behind.
I'm with you. Yes, I understand.
Yeah. So these are
this is a good example. Yeah.
Yeah. So why I gave these numbers, because these numbers were used to explain these locations in our previous paper in 2013. So I'm using and referencing those numbers, exactly those numbers here. Okay. These are the locations where we have polarization, we have H2 emission, and we have HCO plus, everything.
Okay.
So if we go down to next figure.
Remind me what the white dots are then.
Oh, okay, yeah. So white dots are kind of confusing lines of sight because they either not sitting in front of the clump or not behind the clump. So that's why we are calling them just white. We were confused that should we call them behind or should we call them in front. Okay. So that's why we just call them like white. We were kind of confused, not confident about their locations.
Very good. I'm with you. Okay.
Okay. So this is how I am trying to convince reader that I'm talking about 2D behind and 2D in front, not 3D behind and 3D in front. So the yellow star is kind of showing the source of FUV radiation, right? The blue star, that gamma gas. And these yellow stars are the stars which are shining behind the nebula, now 3D behind. Like I have a bigger nebula and there are so many stars higher distance to the nebula. So all the lights from those stars are coming through the nebula.
Yes.
So let's forget about these yellow stars for some time. Just concentrate on the direction, the blue direction, the direction of FUV radiation, and these lines of sight, blue line and red line, segments. Yeah. So this cuboid here is the location of my HCO plus clump.
Okay.
And this reddish is the line of sight which is facing FUV radiation directly, and blue is the line of sight which is not facing FUV radiation directly. So this is what I was trying to tell you in previous figure. Mm-hmm. So this is how I'm dividing the line of sights into blue and red. Okay. And so this was just a cartoon to convince people that what I mean about behind and in front in subclumps. Mm-hmm. So let's go to next figure.
And this looks like the money shots.
Yeah, okay. Figure 5. So figure 5, upper panel, shows the variation of polarization with H2 intensities. So this is part of the first test. We want to see if H2 intensity increases, is my polarization increasing? Because if H2 intensity increases means there is a lot of more H2 formation going on the dust grain surface. And if more H2 formation is going on, then more are the chances of the grain spinning. And if more are the chances of the grain spinning, then more are the chances of the grain alignment. And higher the grain alignment, higher the polarization. Mm-hmm. So if polarization is increasing with H2 intensities, then yes, Edwin Purcell was right that H2 formation do enhance grain alignment and hence give us more polarization. But this plot does not show us a very nice one-to-one correlation.
Right.
And plot A and plot B. B is also the same plot, but with linear regression model fitted with some errors. So actually the thing was in our 2013 paper where we had very less data, less polarization data,
Yeah.
the correlation was really good. But when I added more lines of sight and more polarization data, my correlation is not like very convincing, very good. It's kind of scatter plot. But I think we need more environments, more polarization data in different wavelengths, and then we should compare them with H2 intensities to get some significantly statistically significant conclusions. So I
Right.
think we need more tests on this mechanism. Right now, I'm not 100% supporting that mechanism, but this should be done with more data. But this is the first time we started that, okay, using these observations, we can test the Edwin Purcell's hypothesis or theory directly. We don't have very good correlation, but maybe in our future work, we are going to see something, or maybe we'll never see something.
Both would be
So
interesting.
yeah, so and one thing was that this is just optical polarization. We maybe need to add maybe near infrared polarization also.
Mhm.
So that's what we were lacking in this study. So this was test on Edwin Purcell's theory, but where in 2013 we had good correlation with less data, but we are not having good correlation here. But maybe in future we need more studies to say something. But now figure 6 is another interesting thing. So figure 6 is about the other test. The other test was that we wanted to see how polarization is affected by intensities of HCO plus gas. And why? Because more is the gas, more are the chances of the collision, more is the collision, more will be the disturbance in the grain alignment, and more is the disturbance in grain alignment, more will be the chances to get less polarization, because we need a very nice grain alignment system in interstellar medium to get polarization.
Right.
So there are two populations now, blue and red. So these blue and red colors correspond to those locations or those lines of sights which I showed in figure 3, which I said, okay, behind the clump and in front of the clump.
Uh-huh.
So red ones are the lines of sights where we have polarization and HCO plus intensities, but they are in front of the clumps which are facing FUV radiation directly. And blue are the lines of sight which are behind the clump, where
Right.
they are not facing the FUV radiation directly. So when we plotted delta P, what is delta P here? Delta P is the difference between the mean polarization in, like, there is a mean value of polarization in this PDR. So when and we have polarization measurements for these blue and red dots. So when we started checking the deviation of the polarization of these red and blue dots from the mean value, so that is delta P, that deviation, like P mean minus the P of these dots. So the deviation from polarization is going down
Right.
with the HCO plus intensities, and the slopes of this decay or drop in uh, polarization, I should say now, is different in red dots and blue dots.
Right.
Because blue dots are little bit relatively in the cooler region, so the alignment rate there is not that high than as the alignment rate is in the regions which are directly facing the radiation. So I'm calling those hotter regions. So the red lines of sight which are facing FUV radiation are in the hotter regions. So that's because the region is hot, as you know, that the collision rate directly depends on the square root of temperature.
Right.
So the collision is higher.
Yes.
So higher the collision, higher the possibilities of grain disalignment, and then more drop in polarization than compared to the blue lines of sight which are in the cooler region.
Uh-huh.
So this figure 6 shows that we are kind of supporting these hypotheses. That yes, there are two temperature regions, and we have different drops of polarization with gas intensities in two temperature regions. And very interestingly, when we check the ratios of the slopes of these regions,
Okay.
to the ratios of the temperature, what Thi was showing there, two temperatures, our
Okay.
ratios were very well matching.
Oh, good.
Yes.
Good.
So we are supporting a hypothesis given by Thi that it has a two temperature region, using completely different technique and completely different observations. So this is one thing here that, okay, we are proving, yes, the more is the gas, more is the collision. That's why P goes down. And P is going down differently in different temperature regions. So this is what is shown in this figure 6.
Okay. Very nice.
And I think this was last figure, but there is one thing I want to highlight in this figure. There are these dotted lines, one dotted line at 0P and 2 dotted lines which are intersecting this x-axis at 3.5 and around 4.8. So the dotted line, which is intersecting at 3.5, if you just extrapolate your red line, it will cut somewhere at around this point. Yes.
Yeah.
So red line shows the higher temperature region. So the critical density at which we will start getting drop in polarization is lower in hotter regions than the critical density in the cooler region, because it is around 4.8 or something. So we are also giving some kind of idea on the critical densities of the gas, at which or above which you will start getting a drop in your polarization. So we are giving this hint to people who are doing polarization and gas measurements. So this is another finding in this plot. So yeah, this was it. And I don't think I have more figures in this paper.
No, that's it. There's 6 in this one.
Yeah. So that's it. And if we can discuss our results now, if you have any questions or something. So we kind of successfully tested disalignment theory, but we were not very successful in testing the Edwin Purcell's theory of H2 formation and polarization. But I think we are going to work more on this problem in future. So this is another application of polarization data. Instead of just using polarization data for mapping magnetic fields, we can use polarization data in multibands to test these kind of theories.
Very nice. Very nice. Well, thank you very much, Archana. So you mentioned it a couple of times. Where do we go given what you've published here? And you've already hinted several times at some additional data. Would be good, particularly after going after your first point on Purcell's mechanism. Are there new observations planned? Are there new observatories in the works? Is there stuff people could be doing laboratory astrophysics wise, etc.? So just kind of, where do we go over the next 5 years on resolving?
Yes. So this was one thing. Actually, we have polarization data in several other PDRs. This was just one PDR. It is very diffused. There were very diffused emissions of H2 and HCO plus. We are trying to, or we are going to propose HCO plus in several other PDRs where I have lots of polarization data already. I don't have to do polarization measurements, but I just need HCO plus and other data to do this testing. So we are going to propose on observatories. Like, I think there are some observatories which already have these data, but our resolutions are not matching very well, because I need some kind of similar resolution of all the 3 observations, H2, HCO plus, and polarization. Because if you go to ALMA, it will give you like just small subclumps and very small line of sight, the high resolution. But I have done a kind of survey of these PDRs using several lines, and using a 13-meter dish in South Korea with a resolution of around 50 arcsecond. I may in future use that data to do this testing again.
Cool. Very good.
But that was not analyzed yet.
All right.
So, and just to add one sentence, we are testing one more very famous theory, RAT. So RAT is the theory which describes the polarization, like grain alignment. We are going to test that using our polarization measurements, because if we have polarization in different regions where the amount of radiation is different, what happens to polarization? So in my other paper, which was published, but maybe sometimes in future I'll talk about it, we are going to test that how polarization is affected when I keep on increasing or decreasing the radiation. So it is a direct test on RAT also.
Very nice. Cool. Lots of good future work is going to happen in this over the next couple of years, I think. So
yeah, and with the advent of very good technologies these days,
Yeah, nice to see you. Nice to see you driving it. Very cool. All right, Archana, thank you very much once again for walking us through.
Thank you, Frank.
All right, everyone. Thank you, and we'll see you.
Thank you for having me. Yeah.
Bye-bye.
Bye.